Okay, hello, and welcome to part 2 of Chapter 8, the Ideal Gas Law. Before we start, get your book out and open your book to the first section of 8.5, and you'll find something called Kinetic Molecular Theory. Pause the video and do that now, and then we're going to talk about what you see there. So take the time to read through all 5 of the statements that are listed there. And those 5 statements are the behaviors that we assume gases exhibit if we're going to call them an ideal gas. Okay? And you will never deal with anything in this course that is not an ideal gas. Okay? So these 5 postulates that you see there are the ways that we describe gas behavior. We'll talk about these a little bit in class as well. So as long as the temperature is reasonably high, meaning that the particles have a lot of kinetic energy, so they're moving rapidly, and the pressure is reasonably low so that the particles are spaced out at great distances from one another, then we're going to say, yep, we're talking about an ideal gas. However, think about this. If the gas temperature becomes too low, what would happen to the kinetic energy of the molecules? The kinetic energy of the molecules would decrease, they would move slower, and they would start eventually behaving as if they were about to turn into a liquid. And that wouldn't be ideal gas behavior. Likewise, when the pressure becomes too high, the gases are not going to behave as ideally because they are much more crowded at high pressures, which means they are much more likely to interact. And these 2 problems contradict 2 of the 5 postulates about ideal gases. So here's the ideal gas law, PV equals nRT. Most people call this pivnert. Everybody knows what it means when you're talking in class and you say, all right, we're going to use pivnert on this. And P stands for pressure, as you know, V is volume, N is moles, T is temperature, and the only added factor in this equation is R. And R is a constant that makes the relationship valid. And the units of R depend on the units that we put in for the other 4 variables, pressure, volume, moles, and temperature. We're going to use this value for R, and because of that, these are the units that we must always use when solving a pivnert equation so that our units are compatible with the units of R. So when you write R down in your notebook, make sure you put those units next to it. We like units on values anyway, okay? But these are very important units because if you are given a volume or a pressure that are in different units than you see here, the equation becomes invalid. Now you may notice that really this equation is almost exactly the same as the combined gas law that we have been using for a week or more. Okay, the P1V1 over N1T1 equals P2V2 over N2T2. Really, they are essentially the same equation. However, this form, okay, of the pivnert equation is good for situations where nothing is changing. The other form, the combined gas law, is good when conditions change. Pivnert is better for a single set of conditions. It only has one, temperature, pressure, etc. So, take a look at this question right here. Read it over, pause the video, and see what you can do with that. And then restart, and I'll walk you through it. So the first things to do would be to set up your equation. Just write the equation in its numberless form, just write the pivnert. I like to rearrange before I put values in. It's not a deal breaker if you don't do this, but I think it makes it a little easier. And then I'm going to plug in my values. You will notice that the amount of gas that was given was in grams. That is not compatible with the R value. And so right here, I've converted those grams to moles. I also notice that the temperature that was given is in Celsius. That is not compatible with the units of R either. So we convert that into Kelvin. We then plug in all of the values, and then you can pick up your calculator and figure things out. I'm seeing that we get an answer of 2.1 atmospheres. Let me just show you the unit cancellation here so you can see what's happening. Moles cancels moles, Kelvin cancels Kelvin, liters cancels liters. Atmosphere is the only unit left in the problem, and that's your answer. So I hope this feels doable. This part of gas laws is actually kind of fun, and most students sort of enjoy it because it's not too difficult to plug and chug into the pivnert equation. So here we have another example, and go ahead and pause the video, and you can work it out, and then we will talk, and I'll show you how my answer works out. So for starters, I've written the equation and I have identified the given information. So there you have it. And now I'll rearrange. You'll notice mass has to be converted into moles. So here we go. So here's my conversion into moles of oxygen. And now we'll plug the values into pivnert. And in this case, I get a crazy high pressure of 236 atmospheres. Okay, fine. Looks good. Unfortunately, now that I look at what I'm doing here with this slide presentation, I've done 2 examples of solving for P, and that's sort of unfortunate. But you can rearrange and solve for any of the variables in pivnert. So sometimes you'll be looking for N or V or T as well as P. Let's talk a little bit about gas mixtures. If I have a container and I put in some red gas and some green gas and some blue gas, what we find is, due to their random motion in straight line paths until they bump into something, these gas mixtures fully mix with one another. Okay, they are entirely distributed throughout the container evenly after a short period of time. So let's look at this particular given situation here. We have a single container, and I'm going to do a little bit of a diagram of this because I think it can be helpful. So I'm going to diagram my single container, and I am going to say I have 1.2 moles of argon, 1.2 moles of neon, and I have a P total in my container of 640 torr. Now you'll notice we are lacking some information. You don't know the volume, and you don't know the temperature. So I really can't, in this situation, do any kind of calculations using pivnert. However, think about this for a second. What is the partial pressure of each gas is another way of asking how much pressure is the argon, for instance, contributing to the total of 640 torr. And likewise, how much of the total pressure is the neon contributing. Think about that for a moment. Since there are equal moles of each gas, does it not stand to reason that half of the pressure is due to the argon and the other half of the pressure is due to the neon? If that's what you're thinking, you're absolutely right. Okay? Now, there's a way to sort of, I guess, make an equation about for this, but it's not a fancy equation. Let me show you what it looks like. Here's the equation I have in mind, which is not really a fancy equation. This is nothing but a proportion. And the way it works is the pressure of one gas in a mixture divided by the total pressure of all the gases is equal to the moles of that gas over the total number of moles. I hope that makes kind of good common sense to you. So here is another partial pressure situation, and you actually have more information here. Okay? We have, hold on. We have a volume, we have a temperature, and we have grams of all of these gases. Okay? And so we can, in this case, use PivNert. Let me just explain something to you, though. If I want to calculate the pressure of only the helium, then when I set up my PivNert equation, I should be using moles of helium, RT over V, and that will get me the pressure of the helium. If I'm looking for pressure of argon, I should set up the equation with moles argon RT over V. And if I'm looking for pressure of CO2, set up moles of CO2 RT over V. And that allows me to find the partial pressures of each individual gas. On the other hand, if I want to find the total pressure, all I need to do is take moles total RT over V. Okay? It is also true that if you were to calculate pressure of helium and pressure of argon and pressure of CO2, they would equal the total pressure. And so there's a kind of a variety of ways you could approach this. So why don't you pause the video for a minute and play around with this and see what you can come up with. The first thing I've done here is I've calculated the moles of each of the gases. So I have moles of helium, moles of argon, moles of CO2. And so here we are with all of the values plugged in. I'm going to let you do the verification that that in fact is true. And it should work out within rounding. Of course, I'm going to be rounding these answers a little bit, so they may not add up perfectly, but they should be really, really close. So I can summarize this quickly just to say that partial pressure is not a big deal. You're going to be using equations you already know how to use, including proportions or PivNert, to answer anything asking you about how much pressure does this one gas in a mixture exert, or what would the total pressure be. Either of those ways to approach them will both work. And that's really it for the essentials in Chapter 8. So nice job.